So, we want to know why the energies of the quantum harmonic oscillator are discrete and not continuous. So to start off with, I just want you to consider as a refresher the momentum operator. So in quantum mechanics, it's postulated based off of wave stuff. I'm not going to get into it any more than that. That the momentum operator is equal to minus I h bar times the gradient. And this is in 3 dimensions, but we're considering a one-dimensional problem, so it's just del del x. So, taken together with the fact that the expectation value of an operator's eigenfunctions yields the associated eigenvalue with zero uncertainty, we look for the solution to the eigenvalue equation associated with the Hamiltonian. The Hamiltonian down here is the classical Hamiltonian replaced with the momentum operator applied twice, where px squared would be normally, and then we additionally put in the spring potential as the potential for this equation. So we look at the eigenvalue equation right here, and we look to solve it. So I guess also note too that this is entirely equivalent to the time-independent Schrodinger equation. So then if we make the substitutions, E equals alpha x, or epsilon equals alpha x rather, alpha squared equals m omega divided by h bar, omega squared equals k over m, lambda equals 2e over h bar omega, the eigenvalue equation becomes much simpler, and this is a differential equation, obviously. So now we get on to solving the differential equation. If we went gung-ho and tried to solve this with the power series method, because there's not any other way to do it as far as I know, you would get a very complicated recurrence relationship. So instead of doing this gung-ho, we decide to examine the end behavior of this differential equation. So we look at the end behavior of u, the eigenfunction. The differential equation then becomes this right here, because the epsilon squared term dominates over the lambda, which is a constant. And then we naively assume this is solved by e to the minus epsilon squared over 2. Now I can't give that much of a motivation for why this was chosen, but you'll see that it does work out. You can kind of understand why if you treated epsilon squared as a constant, because then you get one term that in the solution that is proportional to the e to the epsilon squared over 2, and the negative version of that as well. But that's not a very good argument at all. Just note that when you plug this back into the differential equation, this is what you get. You get e to the minus epsilon squared over 2 is approximately equal to 0, which is obviously not true, which just means that e to the minus epsilon squared over 2 is not the solution. However, we're assuming large epsilon, so the last equation holds in the limit, since e to the minus epsilon squared over 2 goes to 0 as epsilon goes to infinity. So now we figured out what the end behavior of the eigenfunction is. So then we assume that our solution is of the full differential equation, not the approximate one, is equal to some function of epsilon, and we're going to call this h of epsilon, multiplied by the end behavior function. So h of epsilon multiplied by e to the minus epsilon squared over 2. So then we plug this back into the original differential equation, and some people might notice that this is the Hermite differential equation. And solving this equation via the power series method yields a recurrence relationship ak plus 2 equals 2k plus 1 minus lambda over k plus 1 times k plus 2, all multiplied by a sub k. So now we're going to analyze the recurrence relationship. Since this solution has to be normalizable or square integrable to be a physical state or physical solution that lives in Hilbert space, we consider the behavior as the behavior of the coefficients as k grows infinite. When this happens, if we go back to the original recurrence relationship, the 1 minus lambda term is negligible, and we get a k squared on the bottom. So we get a sub k plus 2 is approximately equal to 1 over k over 2 multiplied by a sub k. For either the even or odd solution, the k plus second term corresponds to the next term in the series after the kth term. Thus, for either the even or odd solution, consider the k plus 2 term compared to a sub k. So at the start, we're just going to substitute into the original equation up here. Instead of k plus 2, we're going to look at a sub k plus 4. So when we do that, we see that it's equal to 1 over k plus 2 over 2 times a to the a sub k plus 2. Now, we already know what a sub k plus 2 is when we plug that back in, and we get this. So then we do this again. We do the exact same thing we find what a sub k plus 6 is, and then we use the recurrence relationship again. We already found a sub k plus 4, plug that back in here, and we get this relationship right here. Now I figured out what the relationship is here, so it might look kind of complicated, but the final term is always k over 2 plus n minus 2 over 2. So a sub k plus n, the bottom multiplying term ends with the n minus 2 over 2. You can see that with the two terms above, and so on. So now we're finally about to start doing some more with this. We assume that a sub k is equal to a constant, which is not foul play whatsoever, because if you assume that a sub naught, which is, or a sub 1, one of those two, or both of them, are equal to the constants that determine the, the free variables, the constants, and the two independent constants in the differential equation that you solve. Second order differential equation has to have two constants in them. So a sub 1 and a sub naught are those two constants in most cases, but if you take any of the odd coefficients or any one of the even coefficients and say that, hey, a sub 46 is the first constant that determines the rest of it, it's equivalent. So if I say that a sub k is equal to a constant, we're not saying anything different than before. It's just a matter of choosing to define the sum with the a sub 42 term or the a sub naught term, or the same thing with the odd solution. So we assume that, and then we also assume that k is equal to I minus n, and n is equal to 2 times h. It's an even number by definition. And then we get a kind of complicated term, and then we make an additional substitution and say that h is equal to I over 2 minus 1. We plug that in. And this really simplifies it quite a bit. So this means that the a sub ith term is equal to a constant divided by I over 2 minus 1 factorial. So then we plug this back in, and we see that h is approximately equal to the sum of a constant over I minus 1 factorial e to the 2i. And this was done just by multiplying the index by 2, or dividing it by 2, one or the other, to get rid of the I over 2 terms. And then taking the first term out of the sum and shifting the index again. So the second part right here will start at I equals 1. If we subtract 1 from that, we have to add 1 up here, and that gives the second term right here. So then we end up getting this being equal to, so h of epsilon is approximately equal to c plus epsilon squared times e to the epsilon squared. And yeah, that's it. So then we finally get that the at large k, the eigenfunction is approximately equal to some constant plus epsilon squared times e to the epsilon squared multiplied by e to the minus epsilon squared over 2. And this is clearly divergent at large epsilon, which means that it's non-square integrable, which is a problem. So what do we do now? The only way to get a physically acceptable solution, or a solution in eigenfunctions that live in Hilbert space, the series must terminate. So the only way that we can get the series to terminate is for the k plus second term to vanish, or requiring lambda to equal 2k plus 1. Now you see, if you plug in 2k plus 1 for lambda at the top, you get a 0. So when lambda is equal to 2k plus 1, the a to the a sub k plus 2, that term is equal to 0 for either the even or odd solution. So then, revoking the substitution we originally made and replacing k with n, we get the familiar equation E sub n equals h bar omega times n plus 1/2. And this means that the energy that the quantum harmonic oscillator, a particle that is subject to a spring potential, is quantized or discrete. It can only take on values when n is equal to an integer, so 0, 1, 2, 3, 4, 5, etc. And it's important to note here too that when n is equal to 0, so the lowest energy that you can have, you get a positive or a greater than 0 energy, which is kind of crazy. So the lowest energy that the quantum harmonic oscillator, a particle subject to a spring potential, can have is something that's greater than 0, which is very different from what is classical.